Good morning, and thanks for joining my talk. Today I want to discuss some recent work on the calculation of the non-Gaussian PDF for primordial curvature fluctuations. I will start by presenting the setup in which we compute this primordial non-Gaussianities, which is that of inflation with a phase of ultra-slow roll. And I will then discuss two different sources of non-Gaussianity, one of them the nonlinear relation between curvature fluctuations and matter perturbations, basically inflaton perturbations, and the other one, the quote-unquote intrinsic non-Gaussianities of inflaton perturbations themselves, both of which we discussed in these two recent papers. So let's start by reviewing the setup, that of ultra-slow roll inflation. In ultra-slow roll inflation, we have a phase during inflation in which the inflaton slows down as it goes through a local minimum, local maximum configuration in such a way that as the inflaton climbs up the local maximum, it gets to the top just with barely enough speed to get past the local maximum and keep on rolling down the potential towards the end of inflation. And it is illustrative to see this in terms of the slow roll parameters. So we have the first slow roll parameter, which is basically the velocity of the inflaton, and the second one, which is its acceleration. So as you can see, the inflaton is slowly rolling. It accelerates a little bit as it goes close to the local minimum of the potential, but then it heavily accelerates as it climbs up the local maximum, and it just keeps barely enough speed to go past the local maximum and just roll towards the end of inflation. And an important feature here is that this last region here has a constant acceleration, constant second slow roll parameter. It is also illustrative to look at the same dynamics from the point of view of the phase space of inflation. So these are the phase space for this slow roll, ultra slow roll, constant roll inflation with increasing zoom from left to right. So down here would be the slow roll region of inflation. Then the inflaton accelerates a little bit, then it accelerates as it climbs up the maximum. And here you can see in the zoom in that the inflaton retains a little bit of velocity when it gets to the local maximum of the potential, which is the dashed line, and then it makes it through the maximum of the potential, the local maximum of the potential, and it rolls with a constant acceleration, which is a straight line in phase space, towards the end of inflation. Why are we interested in a phase of ultra slow roll at all? Well, basically the idea is that a phase of ultra slow roll during inflation enhances the probability of unlikely large perturbations. So this can be understood, for instance, looking at the evolution of the linear modes for curvature perturbations, which undergo a superhorizon enhancement when they traverse the ultra slow roll region, and this leads to a peak in the primordial power spectrum at the scales that exit the horizon during the ultra slow roll phase. And also, in general grounds, one should expect an enhancement of non-Gaussianity, which is otherwise suppressed by slow roll parameters. Good. So having fixed the setup, let us move to the first source of non-Gaussianity that we are going to study, and that is the nonlinear relation between inflaton perturbations and curvature fluctuations. This is a study. We studied using the delta M formula, which provides a fully nonlinear relation between the curvature perturbation zeta and the inflaton field and velocity perturbations. The idea of this formula from a practical point of view is to compute the number of efforts elapsed from some perturbed field configuration until a later stage of inflation, and from that subtract the fiducial number of efforts starting from unperturbed initial conditions until the same later stage of inflation. And this difference in the number of efforts, hence the name delta n, corresponds up to gradients, therefore this is only valid on superhorizon scales, with the curvature perturbation zeta defined on uniform density slices. From a more technical point of view, this formula is nothing but a change of gauge from the zeta gauge, in which the single scalar degree of freedom of single field inflation is placed in the metric sector, so as a curvature fluctuation, and the delta phi gauge, in which this degree of freedom is placed in the matter sector as an inflaton perturbation. So the delta M formula would basically give you the sum of all the infinite terms in this formula, where I emphasize again that the gradients are neglected. So it only works on superhorizon scales when this curvature perturbation is frozen. How do we put this delta time formula to work to compute a non-Gaussian PDF? Well, the idea is very simple. It's just using the formula for a change of variables in a PDF, which has a term which is the Jacobian of the transformation, just to get the measure of integration properly. And the idea is the following. We assume, and this is an assumption to which we'll come back later, we assume that delta phi is Gaussian. This is motivated by the fact that self-interactions of the inflaton are slow roll suppressed. Therefore, we can compute its Gaussian PDF by just giving its variance, which is the log integral of the power spectrum computed in linear perturbation theory. And with this Gaussian PDF, we feed it into this relation where the nonlinear relation between zeta and delta phi is given by the delta M relation. And this provides a non-Gaussian PDF for zeta, even if delta phi is Gaussian. Let us see an example of this. Consider the constant roll case. So as we said before, this is a regime of dynamics in which the second slow roll parameter is constant. And in this case, the equation of motion for the inflaton has a closed solution. It's an exponential solution. It's a solution of an ordinary differential equation. And this solution, we can perturb and find a close analytical nonlinear relation between inflaton perturbations and delta M, which we recall is equivalent to zeta on superhorizontal scales by virtue of the delta M formalism. We take this formula, we plug it in the equation for the change of variables in a PDF, and we get this very non-Gaussian PDF for zeta, which in the large delta M limit, or in the large zeta limit, has an exponential behavior. It has an exponential tail, which comes directly from the Jacobian. So I've depicted it in blue in all the steps just for you to track where this term comes from. So just this nonlinear relation arising from the delta M formalism is enough to explain exponential, very non-Gaussian tail in the PDF for curvature fluctuations. It turns out that this simple example we can compute analytically, the constant roll case, it's not just a warm-up example, but it's actually very relevant for the scenario we are trying to study. Because as we said before, in ultra-slow roll, when there is a phase of ultra-slow roll during inflation, typically after ultra-slow roll, there is this phase of constant roll, right, in which there is an attractor, which is a straight line in phase space. And therefore, this change of variables relating the enhanced inflaton perturbations into the ultra-slow roll phase and the curvature perturbations is basically the one given by the constant roll approximation we saw before, which interpolates between a Gaussian PDF for small zeta values and a exponential tail for large zeta values. So this is a well-known result, which we also discussed in this recent paper. Also, its equivalence or the conditions for its equivalence with the stochastic delta and formalism, which is related but not identical to the one we have briefly described here. Good. So far we have seen how we can obtain exponential, therefore non-Gaussian PDF for zeta for the curvature perturbation, starting from a Gaussian delta phi, which we assume was Gaussian. And now the natural question is, which we ask in this paper, is okay, is this assumption of Gaussianity well motivated? In principle, one assumes that inflaton fluctuations are Gaussian because, as I said, their self-interactions are slow roll suppressed. But in principle here, we are violating the slow roll conditions precisely because we are introducing a phase of ultra slow roll during inflation. So we could wonder if delta phi is really Gaussian, and if it is not, what impact does this have in the final PDF of zeta? The outline of the calculation we are going to make is the following. Using the inning formalism, which allows to compute correlators of quantum fields in inflation, we are going to compute higher order correlators of delta phi. By higher order, I mean correlators for the 3, 4, that is the ones that are correlators like the bispectrum, which are non-zero for non-Gaussian fields. We are trying to build a proxy of the non-Gaussian PDF of delta phi in this way. I will come back to this later in more detail. And then this non-Gaussian PDF of delta phi, transform it in the way we have just seen into a non-Gaussian PDF for zeta through the nonlinear relation provided by the delta M formalism. Before going into the full result, I want to discuss. Let me go through a kind of preliminary example to illustrate the interplay between this, let's say, intrinsic non-Gaussianity of the inflaton perturbations and the non-Gaussianity coming from this nonlinear change of variables between inflaton and curvature perturbations. To this, consider the change of gauge we saw before, but just cutting at the second order. So we only keep the linear term of the transformation and the quadratic one. Of course, we could add more. We could add all of them actually up to gradients if we use the delta M formula as we discussed before. But for this example, we keep just the linear and quadratic terms. If we now compute the bispectrum of zeta, starting from this formula, the two main contributions, so the two lowest order in perturbations contributions that we had here are the bispectrum of delta phi. So the bispectrum of zeta is the bispectrum of delta phi, plus another term which contains 4 inflaton perturbations inside, which is the product of 2 linear terms times a quadratic term. Let's see what's the physical interpretation for this. So the first term is telling us that there is a contribution to the bispectrum of zeta that comes from the bispectrum of delta phi. Now, the bispectrum of delta phi, of course, is only non-zero if delta phi is non-Gaussian. In other words, this term here, it's an indication of this intrinsic contribution from the non-Gaussianity of delta phi to the non-Gaussianity of zeta. As I said before, it's only non-zero if delta phi is non-Gaussian. In other words, this formula comes from the in formalism. This contribution will only be non-zero if the inflaton field has self-interactions which are encoded in this cubic interaction Hamiltonian that appears in the formula to compute the bispectrum of zeta. This other contribution, on the other hand, this will be non-zero even if delta phi is a Gaussian field. Okay, this term comes from the non-linear relation, in this case quadratic, because we are truncating the series at the quadratic order. But if we kept more orders, it would be a consequence of the fact that we have a non-linear relation between inflaton and curvature perturbations, and therefore, even if the inflaton perturbations are Gaussian, the curvature perturbations will be non-Gaussian due to this term. So what we are doing here, our motivation here is to gauge, to leverage what is the hierarchy between these two contributions to the non-Gaussianity of zeta, which here we are quantifying in terms of its bispectrum. And what we found, analyzing one specific parametrization of the inflationary process in which we parameterize the evolution of the second slow roll parameter, what we found is that this relative importance between intrinsic non-Gaussianity and non-linear non-Gaussianity depends on the sharpness of the transitions between a slow roll, ultra slow roll, and constant roll, which we parameterize with this parameter delta. This is basically the duration in e-folds of these transitions between a slow roll, ultra slow roll, and ultra slow roll constant roll. We scan over values of this sharpness parameter, and then we modified accordingly the duration of the ultra slow roll phase to have, in the different models we studied, here we are going to compare 3, which are these 3 points in parameter space. We modified this duration of ultra slow roll such that the power spectrum is comparable on the 3 models. No? So the peak of the power spectrum is basically the same for the 3 of them. The peak of the power spectrum is, by the way, the color map in this plot. What we found is that for this line in parameter space, the intrinsic contribution to non-Gaussianity is 0. So as long as we remain close to this line, the main contribution to the non-Gaussianity of the curvature perturbations will be the non-linear relation between curvature perturbations and inflaton perturbations. But as we depart from this line, from the solid black line in both directions, the intrinsic non-Gaussianity of the inflaton field will become a more and more relevant contribution. In this plot here, we compare the curly I and curly N terms, so the intrinsic non-Gaussianity and the non-linear non-Gaussianity contributions to the bispectrum of zeta. We find that for this point here, which is close to the line in which the intrinsic component is 0, this is the dashed lines here, so it is this blue line compared with this red line, is an order of magnitude smaller. But for the other 2 cases, both contributions are comparable. So in principle, in those 2 cases, taking only the non-linear transformation as a source for non-Gaussianity, as we would do in the delta N calculation I showed you before, would in principle be a bad approximation in these cases. Right, let me now briefly outline how is the full calculation we did. So not just computing the bispectrum as we showed here as an example, but computing the full non-Gaussian PDF for zeta, which comes from the nonlinear transformation from a non-Gaussian PDF for delta phi. The first step and the most complicated one is finding a proxy for this non-Gaussian PDF of delta phi. And this is complicated because the only information we have about the non-Gaussianity of delta phi is its non-zero correlators. For instance, it's non-zero bispectrum. Reconstructing a PDF from cumulants is a complicated issue. There are techniques like the Gram-Charlier series, but this suffers from convergence issues. So here we tried a different approach. What we did is compute the spectrum and the bispectrum of delta phi using the Inning formalism. We could compute more cumulants, but we stopped at the level of the bispectrum for simplicity. And then we generate numerically a random lattice in position space of inflaton perturbations with the right spectrum and bispectrum as computed using the Inning formalism, right? So basically, imprinting a spectrum and a bispectrum in a set of random data is done through standard techniques in discrete Fourier analysis. So once we have this lattice of delta phi in position space with the right spectrum and bispectrum provided by our Inning calculations, what we do is we sample the lattice to obtain a PDF for delta phi, which is a PDF in position space with the right spectrum and bispectrum. This PDF, which we sample numerically, we use it as an input for the nonlinear relation provided by the delta informalism. And in this way, we obtain a non-Gaussian PDF for zeta that comes from the nonlinear transformation of a non-Gaussian PDF for delta phi. And these are the results we obtain. This panel here, the central panel, corresponds to this example here. So the one in which the dashed lines here, we suspected intrinsic non-Gaussianity was not too relevant. Indeed, we find that the difference between the Gaussian delta phi and the non-Gaussian delta phi, so the PDF that has the right bispectrum, is a small difference, but still this induces a noticeable difference in the non-Gaussian PDF for zeta once we do this nonlinear transformation provided by the delta informalism. For the other two cases in which we suspected that the intrinsic non-Gaussianity of the inflaton field could be comparable to the non-Gaussianity induced by the nonlinearities of the transformation, we indeed find large deviations in the final result for the PDF of zeta because of including these intrinsic non-Gaussianities. However, I should say, as we detail in the paper, that in these two cases, the perturbative control of our method to reconstruct the PDF of delta phi is not totally under control. So these two examples, the left and the right one, should be taken more as a proof of the failure of the standard procedure, but not as the actual result that one should get from a proper calculation. Okay, and this brings me to my conclusions. We have distinguished two sources of non-Gaussianity for primordial curvature perturbations. One of them, the nonlinear relation between inflaton and curvature perturbations. The other one, the non-Gaussianity itself of inflaton perturbations. The first one is treated using the delta formalism, which indeed provides a fully nonlinear relation between inflaton and curvature perturbations up to gradients. So this has to be used on super horizon scales, and it's enough to explain the reported exponential tail in various studies. And the second one requires, as far as we reach, some kind of numerical technique to reconstruct the PDF of delta phi from the calculation of cumulants in the Inning formalism, which is for the moment the most complicated part of this analysis. And with this, I will finish my presentation. Thank you very much for your attention, and looking forward to seeing you in the discussion session. Thank you very much.